Hi, everybody. So in this video, I want to discuss a couple of properties of expected value and variance when we take some combinations of two random variables, say x and y. So I'm going to let x and y denote two random variables. A and b denote two arbitrary constants. Then we've got this property that says the expected value of a times x plus b times random variable y is going to equal a times the expected value of x plus b times the expected value of y. And note that this is a property which holds for any two random variables, x and y, whether they are independent or dependent random variables. So let's take a look at why this property holds. Let's prove this property. So I'm just going to scroll down and kind of reveal one line at a time at the bottom of the screen. So if x and y are two continuous random variables, and let me just say this holds for discrete random variables as well, the proof would be exactly the same, except our integration symbols would be summation symbols. So I'm going to prove this for the continuous case. So x and y are two continuous random variables. A and b denote two arbitrary constants. So first is essentially the definition of expected value. If I want to calculate the expected value of some function of these two random variables, x and y, then the law of the unconscious statistician tells us that we're going to integrate over the full range of values for x on the inside and y on the outside. We're going to integrate this function, which in this case is ax plus by, times the joint distribution for x and y. That's what f is denoting. So here we're just going to set up our integral that we're going to need to evaluate in order to compute this expected value. So next we come down a step, and here's our first step in the proof. Well, what is happening in this step? How did I take this one integral and get two integrals out of it? Well, we took this ax and we multiplied it by f of xy, and then we add to that by times f of xy, and then we can split up the integral into two different integrals because it's a sum. So this first step, we're just distributing terms inside the integral, and then we're using the property that we can break up sums inside of integrals. So now I've got a sum of these two different integrals. So the next thing that I can do is take this constant a, and I can pull it out from inside the integral because it's multiplication by a constant. And I'm going to use that same integration property over here, which says b is a constant. So I can integrate first and then multiply by this constant b afterwards. So now I've pulled out my constants a and b. Next, I'm going to do something a little slick, and that is for this first integral, I'm going to reverse the order of integration. So whether I integrate with respect to x first and then y, I'm going to get the same thing as if I integrate first with respect to y and then x, right? As long as I would adjust my limits on the integral accordingly. And in this case, we're integrating over the full range of values for x and y. So interchanging the limits on the integral is pretty simple. We just go from minus infinity to infinity for both x and y. So I'm going to change the order of integration in this first integral. And I haven't done anything in this second integral. Now I'm just going to pull out my x that I have right over here. And I can pull this out. And I can do the same thing with the y value over here, and I can pull this out. I can't pull it out of the entire integral because I still have integration with respect to y, but at least I can pull it out of the inner integral because the inner integral is being performed with respect to x. So this term y over here is constant as far as this first integral goes. So I can pull it out in front and get a y outside of that first inner integral. And the same applies for x over here. And notice here, we changed this order of integration around so that we can pull this x out from inside the integral, which is with respect to y. let me clear all of these drawings. Okay. And so now if you take a look at each of these integrals here and here, this integral right here is the definition of the marginal distribution with respect to y. And this inner integral right here, this is the definition of the marginal distribution for x. So I've just replaced these integrals with their corresponding notation for marginal distribution for x and marginal distribution for y. And now, let me clear this off. We are basically done. Since all of this stuff right here, this is by definition the expected value of x. And all of this stuff right here is by definition the expected value of y. And we have these constants a and b that were out in front. So now I've shown that the expected value of ax plus b is equal to a times the expected value of x plus b times the expected value of y. And all of these steps, if you missed some of these explanations, I've got them all summarized in the solutions to this worksheet, which are posted up in Canvas. So all of the stuff that I just mentioned about each of these steps, I've summarized down below. And what's really important to note here is that nowhere in this proof did we assume that x and y were independent. So this is a property that holds regardless of whether x and y are independent or whether they are dependent. And so we're going to use this property quite a bit when we get into sampling distributions in the next class and start to think about what do we expect the sample mean? What is the expected value of the mean of a sample from a population? What is the expected value of a proportion that we calculate by randomly sampling from a population? So we'll be using this quite a bit. The next thing I want to talk about are some properties that are just specific to the case where our random variables are independent. So now this is a special case. I'm going to assume now that x and y are two independent random variables. Then we have some additional properties. One is that the expected value of the product x times y equals the expected value of x times the expected value of y. And this property over here, this first one, right, only is true if these random variables are independent. If x and y are dependent, this property generally does not hold. The next couple of properties are relating to the variance of some function of random variables. So if I want to take the variance of a linear combination, ax plus by, we have a similar property that worked out with expected value, but now we have a squared and b squared out front. So it's not just a times the variance of b of x plus b times the variance of y, but we have a squared times the variance of x plus b squared times the variance of y. And this property only holds if x and y are independent random variables. If x and y are dependent variables, random variables, this generally does not hold. So again, we need the assumption that x and y are independent random variables if we want to use this property about the variance. And the last property I want to mention is dealing with a product of random variables x and y. So if I want to calculate the variance of the product x, y, I can take the expected value of x squared times y squared and then subtract from that the expected value of x times the expected value of y squared. So this should look familiar from the variance formulas that we've had. For example, the variance of x we know is equal to e to the x squared minus e of x squared. Okay, so again, be very warned that these properties do not hold if x and y are dependent random variables. Okay, so let's walk through the proof of this second property. So this second property that deals with the variance of a linear combination. Again, linear combinations are going to be things that we are particularly interested in when we start to think about statistical inference. So let's think about this property for variance. And again, here we're going to need to assume that x and y are independent random variables. So I'm going to prove this property that the variance of ax plus by is equal to a squared variance of x plus b squared variance of y. Let me clear my drawings. So coming down below, if we assume that x and y are two continuous independent random variables, then we can use this general property, which says the variance of x is equal to e of x squared minus e of x squared. So in this case, our expression on the inside is ax plus by. So the variance of ax plus by is going to equal the expected value of ax plus by squared minus the expected value of ax plus by squared. So this is the typical property that we have in general with variance of a random variable. And so now our random variable just happens to be a linear combination of other random variables. Okay, so let's take a look at first what happens when we have this second term over here. So I'm going to take a look at that over here. So we can use this property that we just proved up above on the inside. So if I want to calculate the expected value of ax plus by, we just proved that that equals a times the expected value of x plus b times the expected value of y. And now we square this term, and that's going to give me an a squared expected value of x squared, ab times the expected value of x times the expected value of y, plus b squared times the expected value of y squared. So we just distribute this out when we square it. So that takes care of this term over here, the second term. Let's next take a look at the first term over here. So now down here, let's simplify that. So what I have now is ax plus by squared on the inside of the expected value. So let me first square this expression, and that gives me a squared times x squared plus ab xy plus b squared y squared. And now we can use this same property that we proved about linear combinations of random variables to say this is a linear combination of this random variable, and this one over here. So we could break this up as a squared times the expected value of the first random variable x squared plus ab times the expected value of xy plus b squared times the expected value of y squared. Whew. Okay, we are almost done. So now we've simplified, or we've rewritten both the left side and the right side of this differential equation. So again, over here, we had this term, which we proved was equal to all of this. And then we also took a look at this term over here, which we showed was equal to all of this. So now we're going to plug those in down below. So over here is how we simplified the expected value of ax plus by squared. And then over here, I plug in how we simplified the expected value of ax plus by squared. And now I've color-coded the different terms in these expressions so that we can group things together. I'm going to clear my drawing. And so now at this stage right here, we are going to go ahead and group the blue terms together. So I've got this one over here. And so together, they give me a squared e x squared minus a squared e of x squared. And similarly, we get a term that has b squared e to the y squared minus b squared e of y squared. And these terms that have the expected value of x and y, we had this property up above. I didn't prove this one, but if we assume x and y are independent random variables, then the expected value of xy is equal to the expected value of x times the expected value of y. So we can use that right in place here, and therefore that allows us to replace this expected value, AB times the expected value of xy, as AB times the expected value of x times the expected value of y. And now this term is going to cancel this term over here, right? We have this leading negative sign right over here. And so what's left is a term over here that has a squared times ex squared minus a squared times e of x squared. So I can pull an a squared out from both of those terms. I can pull a b squared out from each of the terms on the second sum. And now I've got a squared times e of x squared minus e of x squared, and that's just the variance of x. And now I've got b squared, and this term right here is the variance of y. So now we just proved that the variance of ax plus by is a squared times the variance of x plus b squared times the variance of y. And in this case, we did need to use the fact that x and y were independent, since we needed to use this fact that the expected value of x times y is equal to the expected value of x times the expected value of y, which is true only if we know x and y are independent random variables. All right, that goes through a bunch of properties about expected value and variance for linear combinations of random variables. And we're going to use these properties in the next class.